Hey everybody, hope you're well. Today we're going to talk a little bit more in depth in one of our subjects, probability. We're going to talk about binomial distributions. So we've talked already about a few ways of assigning probability, and using the binomial distribution is going to be one of these. Alright, so just to refresh kind of as previously seen on where we are now, we're talking about probability. And probability is really useful for a lot of reasons, but the reason we find it useful is because it's going to prepare us, it's going to give us kind of the tools we need to get to statistical inference. And so that's where we're trying to go. We've already learned how to do descriptive statistics, but we want to get to statistical inference. In order to do that, we need some of the tools that we don't have yet. So one of these tools is probability. We'll talk a little bit more of the philosophy of it when we get there. For now, probability is where we are. So with probability, we talked about experiments, and an experiment was any process for which we could exhaustively define the outcomes. And some of them are really boring, and some of them are interesting. But if we can define all the outcomes, then they're experiments. So these outcomes are what happens at the end of this process, what we observe. Another name for these was sample points. And the collection of all the outcomes was the sample space, right? So we have a bunch of these, and these all make up the sample space. Once we have these outcomes, in order to try to make predictions and guesses about the world, we want to take these and assign probabilities to each outcome. We looked at a few ways to do this. One was the classical method. That's a CL, it's classical. That's like coin tosses are 50-50. Rolling a six-sided die is 1 in 6 chance, right? Where you just evenly divide 1 by the number of possible outcomes. We looked at the relative frequency method. We learned all about relative frequencies back with descriptive statistics, so if you haven't seen that, I recommend you go back and watch that video. But relative frequencies will meet our criteria for probability, so we just turn these into probabilities. We also talked about the subjective method. Subjective method, also known as making it up, or educated guesses, right, is where we just pick probabilities and assign them. Well, discrete probability distributions are another way to assign probability. These outcomes we talked about can come in a couple different fashions. One would be non-numerical, right, like qualitative data. But if it's quantitative, then we can call that quantity a random variable. And so if we have random variables, then we can separate these into two types. They're either continuous or discrete. Again, this is all backstory. But yeah, in this case, we're dealing with discrete random variables. Discrete random variables come in all kinds. The trick is that they come in chunks, and so that's what we have to remember. One particular type of discrete random variable is the outcome from a binomial experiment. And a binomial experiment looks like this. In order for something to be a binomial experiment, it has to have several properties. What are these? Well, number one, we're going to do an experiment, and we'll call that a trial, kind of a sub-experiment. And a trial has two outcomes. Hence binomial, right? So binomial, if we want to understand this intuitively, bi, like bicycle, means two, and nom means names or classes or groups, right? Like nominal variables or nomenclature, or if you nominate somebody for something, you name them to that position. So nom means name. So two names. Trial has two outcomes. The names we give these are success and failure. But they're just arbitrary. We don't actually apply any weight. Statisticians are pretty non-judgmental, I guess. Maybe that's not true, I don't know. But certainly when we say something is a success or a failure, we don't actually mean that we consider it a failure, right? This could be, an example of this would be heads or tails, right? So if you flip a coin, heads or tails. If you roll a die, there are 6 outcomes, but you can reduce those to 2 outcomes by changing the description. So you could have odd number or even number, and those would be 2 outcomes. Or you could have a low number, 1, 2, 3, or a high number, 4, 5, 6. Alternatively, for example, we could have a case where we're going to make sales calls, and we want to see, is that call a success? Did we manage to sell something, or did we fail to sell something? And so that would be an example of that. Okay, now in each of these trials, in any given trial, the probability of success is fixed. And known. We have to know it, really, to be able to model it. Probability of success is fixed at P, where P is between 0 and 1. Okay, so that's a probability. Now remember, because there are two outcomes, this has an implication, right? What it means is that failure is the complement to success in a given trial, so that the probability of failure plus the probability of success have to equal 1. So this implies that the probability of failure is equal to 1 minus P. That way when we add these together, they add up to 1. That's one of our rules of probability. All right, third characteristic here. 3. We're going to do these trials over and over again, and each trial has to be independent. Right? What does this mean? Well, it means that just because something happened in one trial does not change its likelihood in any other trials. There are some experiments where this is not the case, right? Like if we draw cards from a deck of cards, once we've drawn one, if we don't put it back, it changes the odds of everything else that happens. On the other hand, when you flip a coin, you can't like use up the heads, right? Now, there are two fallacies that people make that ignore this. One is called the gambler's fallacy. The gambler's fallacy says that if you get tails again and again and again, then heads is due, right? The idea here is that it's due, it's due to have some outcome after a bunch of trials. So you get 7 tails in a row, somebody might misperceive the probability of flipping heads as higher than 50%. Actually, that seems that is unuseful. The other fallacy is what's called the hot hand fallacy. And hot hand fallacy, we have runs, right? So in this case, you look at somebody. It comes from basketball, right? You think somebody if somebody is performing better than their long run average at shooting baskets, people say they have a hot hand, which means that conditional on having made 7 shots in a row, somebody might believe that they're more likely to make the next shot. And the evidence suggests that is not the case in basketball. It's certainly not the case when flipping a fair coin, if you know that the coin is fair. That said, if you're doing updating, you may learn something, like, maybe there are only tails on the coin, for example. If you can't inspect the randomization device, that can help. Anyway, in this case, for our binomial experiments, neither of these is true. Each trial is independent, so that probability of success is fixed and continues to be fixed. Okay, our last characteristic. Now, these first 3 characteristics imply that what we have here is a Bernoulli trial. There we go. So these 3 right here, 1, 2, and 3, make up a Bernoulli trial. For it to be a binomial experiment, whoops-a-daisy. For it to be a binomial experiment, then we need to do something. What we need to do is we need to take these trials and we need to repeat them over and over and over again. And so that's what we're going to do. So part 4 here is a trial. The experiment consists of a bunch of trials, and they have to be identical. So it consists of the number of trials we'll call n, identical trials in sequence. And in practice, you could flip all the coins at once, I suppose. So that's a binomial experiment. When we do this, we're going to generate a random variable. That random variable is going to be x. So all of these will spit out x. So taking all 4 of these now. And that x is going to be a random variable that we'll define like this. X equals the number of successes in n trials. All right, so we're going to do this over and over again, n times, and we're going to want to talk about how many successes we got. Now, if we get x successes, and this is important to keep in mind, we are also going to need n minus x failures. That's the number of failures in n trials. And so we kind of have two linked random variables here, right? They're not independent, they're totally dependent on each other, but we have the number of successes and the number of variables. Let's do an example where we have, or let's try to visualize an example where we have magazine subscription customer sales reps, right? So they're participating in a binomial experiment, and they have 3 calls. So we have n equals 3. We have 3 calls, and based on historical data, we know that the probability of success here is 1/3. Okay. Well, one way to look at this is with a decision tree, right, or with a tree diagram. So the first part of this experiment, then, let me scroll down a little bit, get ourselves some space. The first part of this experiment is the first call, right? So the sales rep makes a call. There are 2 possibilities, right? One is that they successfully sell a magazine subscription. The other is that they fail. Okay. The next part of this experiment is the second call. If they succeed, they're going to call again, and now again they can succeed or they can fail. If they fail, on the other hand, again they're going to make a second call, and they can succeed or they can fail. All right, now the last part of this experiment is a third call, and again they can succeed or fail. Here they can succeed or fail. Here they can succeed or fail. Here they can succeed or fail. And this is about as big a tree as I like to make when we're doing tree diagrams, so I picked this for a reason. Alright, now we can take these and call them the outcomes like we've done before, right? Just by following along the tree. We have success, 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 failure. I'm going to omit the commas. Success, failure, success, success, failure, 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 success, success, failure, success, failure, 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 success, and fail, fail, fail. Alright, now to finish this up, we need to define our random variable. And so I'm going to define x here. Remember, x was the number of successes, right? So in this case, I have 1, 2, 3 successes. In this case, I have 1, 2 successes. In this case, I also have 2 successes. And here I only have 1 success. Here I have 2 successes, 1 success, 1 success, and 0 successes. And you can see this is my my set of outcomes, right? These are the outcomes that I have. So the possible values that x can take in this case are 0, 1, 2, and 3. And so we can write that if we want. X is drawn from this sample space. And that makes sense, right? Either they succeed either they don't sell any subscriptions, or they sell 1, or they sell 2, or they sell 3 subscriptions. But now what we want to do is we want to talk about the probability, for example, that x is equal to 2. All right, we're going to try to construct this, and then we're going to try to generalize it to a rule, and then we'll talk about the rule that we have and why it makes sense. Okay, so the way that we've done this before is we've found the probability of all of the cases that fit inside of this event, right? This is an event. It's a group of outcomes that all satisfy this proposition. There's one right here. There's one right here. And there's one right here, right? And so we're going to need to take the probability of each of these outcomes and add them together. That's how we get this, right? So the probability that x equals 2 is going to be the probability of SSF plus the probability of SFS plus the probability of FSS, okay? And so we need to find those probabilities. The way to do that, the way we've done that before, is to just travel along the tree and to think about it intuitively as we go along. I scrolled down a little bit, but you still should be able to see everything we need here. So in this first case, to get to this first one, so let's find this first probability, the probability of 2 successes followed by a failure, in order in this case, right? We want to follow this tree exactly. Okay, in this case we have our first call. There's a 1/3 chance that we will succeed, meaning if we take a large number of calls, a third of them, we would expect to go along this path. So going along this path, there's a 1/3 chance of this happening. Okay, so 1/3 of the calls will look like this first one, right? Now we can think of this like a multi-step experiment, right? Where we have multiple steps. And then, in order to satisfy this to reach this outcome, with the second call, we also need to succeed, right? And so 2/3 of these calls are going to fail, but a third of them are going to succeed. So we have a probability of 1/3 right here. And now, with this third call, in order to get to this endpoint that we want, we need to fail, and 2/3 of the calls will do that. So out of the population of all of these possible calls, 1/3 times 1/3 times 2/3 is the percentage that will follow this path. We can also say that prospectively, that's the probability of following this path in the future. And so if we multiply these, remember, you take the numerators, multiply them together, the denominators, multiply them together, you should get 2/27. And I don't remember what the decimal is there, but it's not that important. We can keep it as a fraction. Okay, so that's one of them, right? We need to find two other ones and then add them together. So let's look at the probability of SFS. Okay. Okay, now maybe let's use a different color. Yeah. Let's use green. The probability of SFS. Okay. Now in this case, we need to succeed with our first call. So there's a 1/3 chance of that happening. And then we need to fail with the second call. So 2/3 of our calls of our calls that made it to this node are going to now go down this way. So we multiply by 2/3. And then, in order to get our second success at the end, in the last minute, when we get to this node, we need to succeed. And so 1/3 of the calls that make it to this node are going to succeed in the end. So we multiply by 1/3 again. And look, hey, it's going to be the same, 2/27. Okay. All right, let's do the last one. I think maybe you can guess what it's going to be, but the probability of failure first, followed by 2 successes. Okay, now at the first node, we want to fail, right? And 2/3 of our calls are going to do that. The majority there. Now, having failed, we need to succeed, and 1/3 of the calls that make it to this node are going to succeed, so we'll multiply by 1/3. And then, in order to get our second success, we need to succeed again. So 1/3 of our calls are going to succeed there. Lo and behold, what do you know? 2/27. The same every time. Okay, now just to wrap up, to get this probability, just to kind of close that loop and feel satisfied about that, we can add these three together, right? It's going to be 2/27 plus 2/27 plus 2/27, which is 6/27. But if we had to do this every time with the tree, it would be complicated and frustrating. And so what we want to try to do is try to draw some generalizations out of this, right? And so we want to ask ourselves, is it a coincidence that these are all the same? And I'm going to tell you that it's not a coincidence, right? You can see that every time we had a success, we had our 1/3, right? Those match. And every time we had a failure, we had 2/3. And as we walked through the tree, we saw that. And so each success has a probability of P, and there are X of these, right? Right? And so we're going to multiply by P X different times, right? So we're going to do P times P times P times P dot 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 X times, right? That's what we did here. X was 2, and so we multiplied by P 2 times, and here we did it as well 2 times, and here we did it as well 2 times. Right? And so every time we run one of these experiments, and we want to calculate a probability of a specific outcome for X, in any given outcome, so for any given outcome, not an X, but any outcome, by which I mean like a sequence, each success has a probability of P. There are X of these. How about failures? Well, each failure, we talked about this a little bit earlier, has a probability of 1 minus P. And so once we get done with our multiplying by P's, and it may come out of order, but by the commutative property of multiplication, it doesn't matter what order they're in, we need to multiply by 1 minus P times 1 minus P times 1 minus P dot dot dot. And then this is going to be the rest of the times, n minus x different times. Now, one of the beautiful things about mathematics, I love it, it's easier, it's terser, is that we can shorten stuff like this, right? If we want to multiply p over and over again, we don't have to write it all the way out like that, right? What we can do to try to shorten this is use exponents, right? If we want to multiply p by itself x times, we can call that p to the x, okay? And if we want to multiply 1 minus p by itself n minus x times, we can take 1 minus p and raise it to the n minus x power. And that will work, right? Let's plug in our numbers from here. So here we had 1/3 was p, right? and then x was 2, so 1/3 to the second power, times 1 minus p, it's 1 minus 1/3, to the n minus x, to the 3 minus 2. This turns into 1/3 squared is 1/9. And 1 minus 1/3 is 2/3. And that's going to be raised to the first power, because 3 minus 2 is 1. And so 1/9 times 2/3 equals 2/27, which is what we found for each of these cases, right? And so this works in this scenario, and it should work always because the intuition is sound, right? Okay, and so what we have found then is we have found a formula for the probability, that's an L, sorry, probability of one particular path to x successes. And that equals p to the x times 1 minus p to the n minus x. Okay, now, in this case, we had to do that 3 times. Why did we have to do that 3 times? Let's scroll back up to the tree. Okay, we had to do it 3 times because there was 1, 2, 3 outcomes that would get us there, right? In the case of 1, if x were equal to 1, we would also need to do it 1, 2, 3 times. Right? We need to calculate it 3 times and then add it. In this case, we only would need to do it once if we were doing x equals 3, and in this case, we would only need to do it once if x equals 0. So, one way to do it is to take it that many times and add them together. Another way is to multiply by how many there are, since they're identical, right? Because we could do either 2/27 plus 2/27 plus 2/27, or 3 times 2/27. And so we already have a formula to figure out this part. It would be really nice if we had a way to figure out how many times we're going to have to multiply it. It turns out that we do have a way to calculate that, right? What we have is we have a situation where we want to find out how many ways there are to pick that many successes. The formula that we use for that is called n choose x. And sometimes it's written like this, and sometimes it's written like, and I generally prefer this notation, n above an x, I don't say over because there's no fraction bar, and n choose x expresses itself as a formula. N factorial divided by x factorial times n minus x, the quantity factorial. Right? It's the number of combinations of that you can get drawing x from n. All right, now factorials, real quick, just a refresher. 0 factorial equals 1. 1 factorial equals 1. Every other factorial equals the number multiplied by itself and then every other number, right? Or 2 times 1, for example. 4 factorial equals 4 times 3 times 2 times 1. 7 factorial equals 7 times 6 times ... times 2 times 1, right? All the way down. So that's how factorials work. It turns out that this is how many ways, how many paths there are to get to a given value of x in n trials, right? One way to think about this is how many places are there to put the successes, or how many different ways are there to put the successes. So in this case, we had 3 trials, and we were looking for 2 successes, the number of ways to get 2 successes. 3 trials, 2 successes, that's going to be 3 factorial divided by 2 factorial times 3 minus 2, the quantity factorial. Now the way that I always do this is I always simplify the bottom first, 2 factorial, 1 factorial, and then I extend the top until I get to the larger of the 2 on the bottom. Right? Because one way to write 7 factorial is 7 times 6 factorial, or 7 times 6 times 5 factorial. So it's kind of like an accordion. You can stretch it out as far as you want on one side if you want. So in this case, I'm going to keep it as 3 times 2 factorial so that I can cancel out and save myself some writing. These cancel out. 3 divided by 1 equals 3. Okay. An intuitive way to think about this one is if you have 3 trials and you want 2 successes, then you have 1 failure. And there are 3 places to put that. That's what this 3 at the end comes to, right? You can put it in the first one, or you can put it in the second one, or you can put it in the third call, but those are the only 3 possibilities. Okay. What if, on the other hand, we had 6 possible outcomes? How many tree paths would get you to 2 successes? Well, now we have 6 factorial divided by 2 factorial times 6 minus 2, the quantity factorial. Again, expanding the denominator first, 2 factorial, or simplifying the denominator first, 2 factorial times 4 factorial. Now I'm going to extend the top just to the 4 factorial, because that's the way to do this with the least amount of writing. So now I have 6 times 5, that's a 5. It's an ugly 5, but it is a 5, I guarantee. 6 times 5 divided by 2 factorial, 2 times 1. 6 times 5 divided by 2 times 1 equals 30 over 2. That equals 15. Okay. So this is how you calculate the number of paths that will get you to a given outcome in a given scenario. Okay, so in this case then, we figured out it was 3. We got 3 times 2 27ths. But we also figured out that what we really want to do is we want to take, intuitively, the number of ways to get x successes times the probability of any particular way to get x successes. And all this does is it finds all the probabilities that we would want to add, which happen to be the same, and then adds them all up together, right, via multiplication, which is really just, addition with gas, right? Cooking with gas with addition. So this is the formula that we want. The formula that we have satisfies this. So this is the binomial probability distribution. Very fancy. All right, f of x, and remember f of x, just like we talked about, I believe in the last video, is a function. It takes x and you grind it through the f machine and it spits out a probability. F of x, this is your probability. Okay, so f of x equals the number of ways to get x successes in n trials, which is n choose x, times the probability of any particular way to get x successes. P raised to the x times 1 minus p raised to the n minus x. All right? So that's the formula, and that's why it makes sense. It's not just nonsense. I mean, it matters. It fits. So for the example we did above, we showed that the probability of getting 2 calls was 3 choose 2 times 1/3 to the second power times 1 minus 1/3 to the 3 minus 1 power, which equals 3 choose 2 is 3. We did that earlier. Times 1/9 times 2/3, which is 3 times 2 27ths, which is 6 27ths. Right. If you want to reduce that, you can. What is that? 2/9, which is 22%, 22.2%. I'm doing that math in my head, so hopefully that's correct. Let's do a few more just to work through these. So f of 1, what's the probability of getting 1? Well, it's going to be 3 choose 1 times 1/3 raised to the first power times, and I already subtracted 1 minus 1/3 once before, so I'm not going to do that math again. This is 2/3 raised to the 3 minus 2 power. This turns into 3 choose 1. Let's 3 factorial divided by 1 factorial times 3 minus 1 factorial times 1/3. Oh, sorry, this should be 1 here. That's a mistake. Times 2/3 raised to the second power, 2/3 squared. equals 3 factorial, let me do the denominator first, 1 factorial times 2 factorial, 3 times 2 factorial, times 1/3. Now squaring this, you get 4/9. And if we cancel these out, you should see that this will turn out to be the same. 3. So this turns into 3 times, and then multiplying these, you get 4/27, which is 12/27, which is, what's that, 4/9? 4/9. There we go. That's 44.444%. All right, the last two, I'm running out of space here, but we'll be all right. F of 0 equals 3, choose 0, times 1/3 to the 0th power. If you remember, exponents to the 0th, or things raised to the 0th power, are equal to 1, times 2/3 to the 3 minus 0. 3 choose 0 is how many ways there are to get 0 successes in 3 trials, and there's only going to be one way. It's going to be fail, 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 right? But just to expand it, I can show you. We have 3 factorial over 0 factorial, which is 1 by definition, times 3 minus 0, the quantity factorial. Oop, not times, right? Times 1/3 to the 0, which is 1, times 2/3 to the 3rd power, 2/3 cubed, which equals 3 factorial divided by 3 factorial reduces to 1, times 1, times 2/3 to the 3rd is 8/27. Which that doesn't reduce, but that's 30%, 0.296 continuing. And then one more. They should all add up to 1, but we'll do the last one just to get it down. F of 3 equals 3, choose 3. Again, that's going to be 1 for the same reason. There's only one way to do it. You can expand it if you want to show it. Equals 3, choose 3 times 1 to the 3rd times 2/3 to the 3 raised to the 3 minus 3. So you get 1 times 1/3 cubed times 1 again, which turns into 1/27. So we have 1/27 plus 8/27 is 9/27 plus 12/27 is 21/27 plus 6/27 is 27/27. So sure enough, they add up to 1. All right, so that's how we work with a binomial probability distribution. Let me just lay out a couple properties of the binomial distribution real fast, just so you don't have to do some heavy lifting later. So, what can we do with a binomial distribution? Well, we looked earlier at how to calculate the expected value and variance of these random variables. In this case, if you know that you have a binomial distribution or a binomial experiment, then the expected value of a binomial variable is a simpler thing. You can calculate it the other way, right? The way we calculated it before was as the weighted mean, right? Mu, or the expected value of x, you can write it either way, is equal to the sum across I of across the outcomes of the value of the outcome times the probability, right? Is the weighted. It's a weighted mean where the probabilities are the weights, and the weights add up to 1, so we suppress the divisor. But in this case, because they're independent, you know that 1/3 of them in this example are going to be successes on average, right, in the long run. And then you just need to multiply by how many you have. So it's kind of intuitive, but for a binomial random variable, it's just going to be n times p. Okay, so that captures that, n times p. If you want to calculate the variance, again, we can do it the long way, but we don't have to. The long way, if you recall, was sigma squared, also known as the variance of x, equals the sum across outcomes of the squared deviation from the mean, just like we did with variance for samples, weighted by probability. But if you know it's a binomial variable, then you can shorten this. Much simpler. You don't have to calculate all the f of x's, you just have to know the underlying parameters. It's n times p, which you already calculated from mu, times 1 minus p, and that'll get you your variance. All right, in this case, we had 3 trials, and so n was equal to 3. and p was equal to 1/3. And so here our mu equals 3 times 1/3 equals 1. Right? On average, in 3 sales calls, in the long run, you're going to get around 1. Right? Our variance then is going to be this 3 times 1/3 times 2/3, which we already know this is 1, and so that's going to be equal to 2/3. There you go. Cool. So that's all the things you need to know about binomial random variables, right? So we have a series of Bernoulli trials. They're all independent. They have a fixed probability of success. Success or failure are the only 2 possible outcomes. We did it with a tree. When you get to larger n, right, like a tree is just impossible to deal with, and so we wanted to come up with a formula that would allow us to calculate the probability of a specific outcome. And so the formula we found was this one right here, right? It's the number of ways to get x successes and n trials times the probability of any particular way to get x successes. And if you do that every time, you'll get the correct probability of x successes. All right, guys, thank you very much, and I will see you again soon. If you have any questions, as always, let me know. I'll be happy to help and happy to answer them. Thanks, guys.